Okay, now we'll also now describe another important parameter of thermodynamics, that is heat capacity. Now there are two kinds of heat capacities, that is constant at constant pressure and at constant volume. So let's define heat capacity. C equal to Q by del T. We have been talking about this del Q term in, always keep this formula. This Q term in first law of thermodynamics. This Q term is very important, and how we define that Q term, or sometimes we need to substitute that Q term. I have already told you that this del Q cannot be calculated directly. So you have to have some kind of substitution in terms of other measurable quantity by which you can actually calculate del Q. So this is one of those things. So what does it mean? That heat added to the system by the change in temperature. So once you add heat to the system, there is a subsequent change in the temperature, right? Or withdrawn from the system, there is a change in the temperature. If the heat is withdrawn, the del T will be negative because the final temperature is less. If heat is added, so del T is positive. So anyway, but whatever it might be, so heat capacity is defined as the ratio between the heat added or subtracted to the system by the incremental change in temperature. Now these, always keep in mind that there are three important parameters, right? I have told in the beginning, P, V and T. What happens to P, V and T when this occurs? So for our way of calculation, or for ease of calculation, normally heat capacity is defined either at a constant pressure or a constant volume. If this entire process is done at a constant pressure, then we define Cp is equal to Q by del T constant pressure, or in the differential form del Q del T at constant pressure. Or if it is done if keeping the volume constant, so we define Cv is equal to Q by del T at constant volume is equal to del Q del T at constant volume, right? So let's see how this substitution affects the first law of thermodynamics. Okay, so for example, I'll just erase this part. Let's talk about Cv. So at constant volume, we have already said Cv equal to del Q del T at constant volume. This differential is done keeping the volume constant. So we have defined, now let's go back to the first law of thermodynamics. You have del U, del Q and del W. What happens at constant volume? Do you really do any work if your volume is constant? The answer is no, because P del V equal to 0 at constant volume. So what happens here is du equal to, if you substitute del T, it becomes Cv del T, or du dt becomes your Cv. So this is an alternate definition of heat capacity at constant volume. So del U del T is equal to Cv. So if you know Cv, you can actually calculate the internal change of energy. Okay, so this is what we have at constant volume. Now let's go back to constant pressure. At constant pressure, you have del Q del T equal to Cp, right? So if I substitute it here, what do we get? See du and minus del W, we have already talked about this. At constant pressure, del W is P del V, right? So del U plus P del V, we have defined it as del H, right? As enthalpy. U plus P equal to H. So in differential form, it will be del U plus P del V equal to del H. So if you just take it back from here, du plus del W is equal to del Q, or we have over here del U plus P del V is equal to del Q, or if we put it back, del H is equal to Cp dt. Okay, so this is important. So enthalpy, this is a very, very important formula. This is very, very important. So enthalpy can be calculated from the heat capacity of the system over a range of temperature. Okay, so del H is equal to Cp dt is one of those important formula which enable us to calculate enthalpy at constant pressure. Always remember this. You always check. This Cp always stands for constant pressure. Never apply that del H equal to Cv dt. It's wrong. For a constant pressure, enthalpy change can be accommodated or can be calculated from Cp dt. Right? Fine.